Because we know they are complex, we can just replace the x by a complex number. So replace x, write u plus vi, and just follow up. Elementary algebra, and you can simplify, and you will have two components. What we call the terms that will involve an I, the terms that will not involve an I after simplifications. They are called the real and the imaginary part. Both are real, they are just names. But they are surfaces. So you have to force the real part to be 0 and the imaginary part to be 0 at a common point. Well, can you graph the real part? Just graph the surface RUV. So just call it whatever, say W equal RUV. Take your calculator, and I asked my students to do it. They use a Maple there, and they did it. And here is the graph for the real part. That is the graph for the real part. It's also nice because that's another opportunity I have to have a feeling of what degree 4 means. Degree 4 means that it means that you take your bag and you go into a circle. You will go up 4 times and you will go down 4 times if the circle is big enough. But remember, keep in mind what we want. We want values on which this surface is equal to 0. So you have to go to sea level and cut it horizontally, and that's what we call level curves. Can you imagine what you will see? Ready? Okay, let's see your imagination was right. Cut it in. Here they are, the level curves. The solutions have to be there. This is where the real part is equal to 0. They say, well, but we have to place also the imaginary part. So you have to drop it in 3. This is the graph in 3 dimensions of the imaginary part. Carry it at the sea level. But both have to be 0 at a common point. Well, you know what I will do. Take one at the top of the other. And here we have the 4 complex roots, the points of intersection. Here they are. They are the four complex roots that we didn't see before. They are just the points of intersections of the real and the imaginary part. There is no reason for not seeing them. Now, if we don't see them, it is because we don't open our eyes well. Just for fun, I did it for the degree 6. That's the real part of the degree 6. That's the level curves. You're expecting 6 solutions. This is the imaginary part. Level curves. Points of intersection. I know I should be using 2 different colors, but I didn't have too much time really. But there are the 6 solutions. But let's go back to a little bit to something else. What else can we say about polynomials? Well, probably the most popular topic in mathematics is number theory, maybe. Primes are in the middle of everything. What primes and polynomials have in common? Well, they are friends, for sure. We have a classic result. If you take a polynomial, the famous polynomial, that x squared plus x plus 41, the first 39 values that I'm talking about whole numbers for x only, the first 39 values will give you a prime number. I mean, that's kind of, I would not say strange, because that's beauty. That was really an invitation to find a polynomial that was going to produce only prime values. As we all know, that polynomial doesn't exist. So I was teaching an elementary number theory class, and I just proved that the polynomial, by the way, when you try 40, that's what you will get, 41 squared. And someone will say, but at least 41 is prime. Yes, we can say something about that. It's a classic result. No polynomial with whole coefficients will produce only prime images. Then I proved in the class, it was a classic proof, and I proved that any polynomial will have at least one complex image. And one student, I guess, I don't know what he said, okay, how many complex? I said, well, at least one. He said, well, how many? I said, well, at least many, I said. Then I went to my class and I said, I just reviewing that same proof, I didn't change the proof. I said, oh, well, the conclusion should be stronger. Any polynomial will produce an infinite number of images. Then I went back to the next day